Okay, so in the last section we talked about tests about a population proportion. In this section we're just going to expand our test of significance to population means. So after this section you'll be able to basically state and check the random condition, the 10% condition, the normal/large sample conditions for performing a significance test about a population mean. You're going to be doing a significance test about a population mean, and then we're going to use a confidence interval to draw a conclusion from a two-sided test about a population mean, just like we did last section with a population parameter. All right, so let's just do a brief introduction of what we're going to be going over. Confidence intervals and significance tests for a population proportion are based on z-values from the standard normal distribution. So what you're going to be learning in this section is basically the same thing that you did with proportions. We just are going to have to take a look at a couple of different curves. So number one, we know from the previous section that proportions use z-scores, and we also know that whenever we did tests and we did population means, we use z-scores when we knew the population standard deviation. Most of the time you're not going to know the population standard deviation for means, so inference about a population mean mu usually uses a t-distribution, because remember that's whenever we don't know the population standard deviation, with n-1 degrees of freedom. In rare cases, you'll know the population standard deviation, but just get used to basically, you're going to read the question carefully, but assume that you're using a t-distribution with the population mean unless they, for some reason, give it to you. We learned how to construct confidence intervals for a population mean in section 6.3, and then we'll also take a look at how we can use the confidence intervals to test a claim or use a significance test about an unknown population parameter mu. All right, so let's just take a look at an example. A company claimed, and we did this I think in a previous section, a company claimed to have developed a new AAA battery that lasts longer than its regular AAA batteries. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. However, they decided to take an SRS of 15 new batteries, and they found out that they had lasted on average 33.9 hours with a standard deviation of 9.8 hours. Does this give convincing evidence that the new batteries last longer on average? Now just remember that you're going to come up with this question, or the alternative hypothesis they come up with it before they actually take the sample. So they didn't take the sample and then say, hey, we actually think they last longer. They said, hey, we think it lasts longer. Then let's take a sample and see if we have enough evidence that the new batteries actually do last longer. So what would that null and alternative hypothesis? Remember, it's always in terms of the population, never in terms of the sample. So we're testing the alternative that it's equal to 30 hours. That's what we know from the past. Versus the alternative, we're saying, hey, we actually think the new batteries last longer than 30 hours. Notice how mu is defined. It's the true mean lifetime of the new deluxe AAA batteries. Okay, now just take a breath. Don't go any too crazy or think that this section is going to be much different than the last one. This section is exactly like section 8.2, only instead of using proportions, we're going to use means, and instead of z-scores and normal distribution, we are going to use t-scores and the t-distribution. So in order to carry out a test for mu, or an unknown population, for mu with an unknown standard deviation, there's going to be a few things that we're going to be different. The major steps will stay the same, so it's still a 7-step process, but we're doing a test statistic with means instead of proportions, and that's why I said we're going to be using the t-distribution instead of the z-distribution. And then just remember, with means, your normal condition is a little bit different, so you just don't want to mix those two up. Okay, so in the previous chapter we introduced conditions that should be met before we can construct a confidence interval. Why? Why do we have to meet these conditions? Number one, remember we have to be able to, the simple random sample allows us to use inference for a wider population. The 10% condition allows us to use the standard deviation, divide by the square root of n, and then remember that we have to have the normal condition. Before we can find any probabilities or confidence intervals, we have to make sure that the population is normally distributed. So before we do a test about a population mean, we still have to have a simple random sample. The population still has to be more than 10 times the sample size, and you have to check your normal condition. Now remember that since this is a t-distribution, we're going to be using the sample size to check this. How can we check and see if means have a normal distribution or normally distributed. Number one, if the population is normally distributed, you're good to go. Remember that the central limit theorem applies as long as the sample size is larger, which is greater than 30. If it is smaller than 30, a couple things you can check. If n is less than 15, you want to check a normal probability plot or a histogram. We're looking for normality, so you would state it's linear, therefore approximately normal, or a histogram. If it's between 15 and 30, you're going to look for a box and whisker plot, and then just make sure that you're going to state there's no strong skewness or outliers in this case. And that's because, remember, with a box plot, we never prove a box plot is approximately normally distributed. We can't say that. We can just say that it's symmetrical. Just make sure that if you're doing one of these two bottom questions, you have to show a sketch of the graph. All right, so let's just take a look at an example. A classic rock station claims to play an average of 50 minutes of music every hour. However, it seems that every time you turn on the station, there's a commercial playing. So to investigate their claim, you randomly select 12 different hours during the next week and record what the radio station plays in each of the 12 hours. So here is the number of musics in each of the hours. So 12 hours, basically how long they played music. Check the conditions only for carrying out a test of significance of the company's claim that it plays an average of 50 minutes of music per hour. All right, so just take a look at the directions carefully. In this one, we're literally just checking the conditions. Well, how do I know what conditions to check? Well, number one, we know that we're taking a look at average amount of minutes that they're playing. So we know that this is means and not proportions. And then we also are not given a population standard deviation. So we know that we're going to be using a t-distribution in order to check this. All right, so first condition, no matter what you're using, means, proportions, is always an SRS. In context, it's a simple random sample of 12 different hours during the week. Same thing with means or proportions, still independence. There's more than 120 hours during the week in context. And then the approximately normal condition. So in this case, we only have 12 different samples. It doesn't say anything about the population. So we're going to use the normal probability plot. Make sure you draw a sketch, doesn't have to be anything fancy, and then the statement that the normal probability plot is linear, therefore the sample is approximately normal. That part is important because you're showing how you know it's approximately normally distributed. All right, so once we have our conditions done, we've decided the test that we're going to use, and we have our null and alternative hypothesis. What test statistic do we use in order to see how far our sample is away from the true population? So this is the same formula we've used. We're taking our statistic, seeing how far away it is from the parameter, or basically your null, and then dividing by the standard deviation of the statistic. In this case, since we're using a t-distribution, we are going to use since we're using a t-distribution and we're using means, what we're going to do for our standard deviation is we're going to take the population standard deviation divided by the square root of n. However, most of the time, like I said, since the population standard deviation is usually not known, this would be if you had z-scores, we're going to use the t-distribution and just replace the population standard deviation with the sample standard deviation divided by the square root of n. Now, please make sure that when you do this with the t-distribution, you're always stating the degrees of freedom so we know what t-curve we're looking at. Okay, so when the conditions are met, we can test our claim about a population mean using a one-sample t-test. To make sure we have an SRS, the population has an unknown mean mu. We're testing the hypothesis. Notice how this is the population standard deviation against what we already know. We're using the one sample t-statistic. We're taking our sample, seeing how far away it is from the mean, dividing by the sample standard deviation. Remember, the p-value is the probability that you get this t-statistic that extreme or more extreme, and as stated by the alternative hypothesis, and it's always going to be based on. It's important to state the degrees of freedom so we know exactly what t-distribution we're looking at. And just remember, when we're checking to see if the alternative is greater than, it's always the upper tail probability, the probability that it's that t extreme or greater. Remember, if it's less than, we're checking to see what's the probability that we get this t-statistic far away from the mean or less. And then if it's not equal to, what's the probability that I get that t-statistic or higher, or that t-statistic or lower. Okay, and then just always remember that the null is written using mu. And what's going to be on the AP exam formula sheet. So remember from the previous section that you have your general formula for a test statistic. It's how far away the statistic is from the parameter divided by the standard deviation of the statistic. You have your confidence interval formula. It's the statistic plus or minus your critical value times the standard deviation of the statistic. So you're just going to fill in what we know here. If we're talking about x bar, parameter mu, in this case, since we're talking about sample means, that's the standard deviation of the statistic. You're just going to have to know whether or not you have the population standard deviation. If you don't, you're going to replace that sigma with S of x. All right, so let's just take a look at our back to our battery example. So the battery company wants to test the null, the mean is equal to 30 hours versus, hey, they actually think that they've made an improved battery, the alternative that the new mean is greater than 30 hours. Based on a simple random sample of 15 new AAA batteries, they found the mean lifetime of the sample to be 33.9 hours and the standard deviation of the sample to be 9.8 hours. So what does that test statistic look like? How far away is our sample actually from the population mean that we've known from the past? So we have our sample 33.9, subtract it from 30, that's how far away it is. Notice the standard deviation on the bottom is the sample standard deviation divided by the square root of the sample size of 15. Keep in mind that we're using t, the test statistic, because we don't know the population standard deviation. So this tells us it's 1.54 standard deviations away from the mean. And then just remember in this case, in order to find the p-value, the p-value is the probability of getting this specific t-value or larger, because that's the direction stated by the alternative, because we're going to say, hey, we actually think it's greater than 30. So what's the probability that t is greater than or equal to 1.54? So here's our mean, basically, of 30. Here's our test statistic t. What's the probability that I get this test statistic or more extreme? Okay, so remember that since we're using a t distribution, you can either use your graphing calculator or you can use the table. So you'd go the degrees of freedom is 14, that's n minus 1, and then you would say what's the upper tail probability here? Okay, so the upper tail probability is between 0.1 and 0.05. Okay, so 1.54. Okay, it's somewhere in here. So the p-value is going to be somewhere between 0.1 and 0.05. It's not exact because our t-value that we have right here it's bigger than 1.345 and smaller than 1.761. So it's going to say somewhere between 0.05 and 0.1. That's why it's actually easier just to use your calculator, because then you get the exact p-value rather than having an estimation. So the table B, remember, gives you a range of possible p-values for significance. We can still draw a conclusion from the test in much of the same way as if we had a single probability by comparing the range of possible p-values for our desired significance level. Okay, so also table B, remember, gives probabilities for t-distribution with degrees of freedom from 1 to 30 and then does 40, 50, 60, 70, 80 up to 1,000. The bottom row gives the probability for degrees of freedom equal infinity, which corresponds to the standard normal curve. Remember, if the degree of freedom isn't provided in the table, use the next lower one. So if it's 44, go down to 50. Or sorry, 44, go down to 40. If it's 56, go down to 50. If it's 61, go down to 60. If it's 89, go down to 90. All right, and then get what your p-value should be. The table B shows probabilities only for positive values of t, so to find a p-value that's negative, just use symmetry and find the equivalent positive test statistic t, and it'll give you the exact same answer. So if you come up with negative 1.32 on the table, you're going to look at positive 1.32. But I would highly suggest using your graphing calculator, much easier. So just as a previous recollection, remember from our previous sections where we learned how to find our p-values using a t-distribution, you would just do t-CDF, lower bound, upper bound, degrees of freedom. In this case, our lower bound is 1.54, our upper bound is 1,000 because we want it to be greater than that, and our degrees of freedom is 14, and then it gives us the exact p-value. You can also run a test on your calculator to get your p-value, similar to we did in the last section, and your test statistic. Just remember, it's not going to count as your work. So if you're using the test feature on your graphing calculator, totally fine. You just need to make sure that you show the work for the free response section, and then in the multiple choice, you can go ahead ahead and use the calculator the whole time.